In the preceding chapter, our concern was to describe the motion of a particle in space quantitatively. We saw that uniform motion needs the concept of velocity alone, whereas non-uniform motion requires the concept of acceleration in addition. So far, we have not discussed the question as to what governs the motion of the bodies. In this chapter, we will discuss about this basic question. Let us first guess the answer based on our common experience that to move a football at rest, someone must kick it. To throw a stone upward, one has to give it an upward push. And there are so many examples. And from these examples, it is clear that some external agency is needed to provide force to move a body from rest. Likewise, an external force is needed also to retard or stop the motion. In these examples, the external agency of force is in contact with the object. This is not necessary always. A stone released from the top of the building accelerates downward due to the gravitational pull of Earth. Similarly, a bar magnet can attract an iron nail from a distance. This shows that external agencies can exert force on a body even from a distance. So we can say that a force is required to put a stationary body in motion or stop a moving body, and some external agency is needed to provide this force. This external agency may or may not be in contact with the body. But what if a body is moving uniformly? Is any external force required to keep a body in uniform motion? Aristotle's fallacy states that an external force is required to keep a body in motion. But it was proved wrong by Galileo and Newton. Let's discuss the Galileo's observation. A ball released from rest on one plane rolls down and climbs up the other in the absence of friction. The heights of the ball on both the planes are the same, but in practical situation, the height on the second plane is always less than but never greater, and it is because of the frictional force, which we will study later on. See the case 1, case 2 and case 3. Here the height of the second side is changed. And all these cases are in the absence of friction. And you can see that the ball rolls down and continues to move in the horizontal direction through infinite distance in the absence of frictional force. So Galileo thus arrived at a new insight on motion that had proved the Aristotle fallacy wrong. The state of rest and the state of uniform linear motion are equivalent. In both cases, there is no net force acting on the body. It is incorrect to assume that a net force is indeed needed to keep a body in uniform motion. And to maintain the body in uniform motion, we require an external force to counter the frictional force so that the two forces sum up to zero net external force. If the net external force is zero, a body at rest continues to remain at rest and a body in motion continues to move with a uniform velocity. And this property of body is called inertia, means resistance to change. Inertia is the inherent property of a body due to which it resists a change in its state of rest or of uniform motion. And mainly it has three parts: inertia of rest, inertia of motion and inertia of direction. And mass is the measure of inertia. Heavier objects have more inertia and lighter objects have less inertia, means less opposition. Inertia of rest. The tendency of a body to remain in its position of rest is called inertia of rest. As shown, examples of inertia of rest: a passenger in a bus jerks backward when the bus starts suddenly, because the passenger tends to be in inertia of rest, whereas the bus is moved away forcefully. Inertia of motion. The tendency of a body to remain in its state of uniform motion in a straight line is called inertia of motion. Example: when a moving bus suddenly stops, a person sitting in it falls forward. As the bus stops, the lower part of his body comes to rest along with the bus, while the upper part of his body continues to remain in motion due to inertia and falls forward. Inertia of direction. The inability of a body to change by itself its direction of motion is called inertia of direction. For example, when a bus takes a sharp turn, a person sitting in the bus experiences a force acting away from the center of the curved path due to his tendency to move in the original direction. He has to hold on to a support to prevent himself from swaying away in the turning bus.